The following is a presentation of NoVA Hackers at ShmooCon Epilogue 2014, hosted by Mach37, brought to you by ComputeCycle.
All right, hi everybody. I'm Hank, and this is PathWell. Thanks for the NoVA Hackers for putting this together. Thanks for Mach37 for hosting us. Thanks for ShmooCon for rejecting my talk and giving me feedback to make it better to give to you guys today.
Did you get your feedback?
Yeah.
Aw, Chris doesn't love me.
So the TLDR of my talk is make user passwords 5 to 6 orders of magnitude harder to crack.
Awesome, thanks.
Yep, there you go. You're out of here. Actually, that's the TLDW of my talk. And I'm talking about doing this without changing to a stronger hash algorithms, which is what you should do, without forcing people to use longer and longer passwords, switching to passphrases, etc., which are all things you ought to do, but the reality is we don't. So this is something that should be able to work with the technologies and user behaviors, well, with the exception of the user behavior we're about to change of today. Just a little bit of background stuff. I build stuff and break stuff. NoVA Hacker, etc. A little bit of background on you guys. So how many people here, let's see, have ever seen my coworker Rick Redmond / Minga give a password cracking talk? Like why your password policy sucks, or why corporate password policies suck, etc. Okay, good, a couple of hands. The new conference up in New York a couple months ago. No, okay, cool, so you'll see a longer and better version of it here. So I've had some of the ideas that led to PathWell rolling around in my head since around 2010, but I didn't get a chance to actually make them into something real, and, well, I didn't get a chance to develop the ideas to see if they were something useful, and then build a proof of concept until this last year under Cyber Fast Track. And when I say my coworkers did more of the work actually building the thing than I did, so that's awesome because I just get to stand here and take credit. Got more detailed credits towards the end of the talk. I'm gonna, don't save your questions for the end, unless you really want to, but for the most part, please feel free to raise your hand or blurt out questions. I am going to move through a little bit of computer password cracking history background, cover about 15 years in less than 15 minutes. So I'm going to necessarily strip out and trim down and generalize and condense a whole bunch of details. But if I don't do that, you can't, if I don't catch up, if I don't recap where we are and how we got there, then talking about moving forward is not gonna make a lot of sense. But please interrupt me and raise your hands, etc. And I'll either answer you on the spot or tell you that your answer is 2 slides away and just wait for it, or tell you that it's too big of a diversion and that we'll talk about it after the end of the main presentation, if there's still time, or out in the lobby. But I know I can't sit through a presentation and remember the question that I had in the first 5 minutes, and if I never saw the answer to it, it's just lost, and I think of it 2 days later, like, oh, damn, I should have asked him so-and-so. So please go ahead. So classic password cracking, and I mean taking us through like the 90s to early 2000s, we're talking mostly about offline cracking. I'm not talking about online brute force login attempts. I'm talking about getting a set of encrypted passwords somehow, password hash, and then trying to beat on them. Historically, naive brute forcing was not really feasible. I mean, going through the entire password space from AAA to ZZZZ, or AAA to exclamation point, exclamation point. Computing power just wasn't there relative to the strength of the hash types to be able to do that exhaustively and naively. So what the approaches that people would use are, and many refinements on picking word lists intelligently, dictionaries, common words and phrases and names and blah, 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 and mangling rules. How am I going to manipulate every entry in my dictionary to flip the case and substitute letters and insert things and flip positions and blah, 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 and figure out the most effective word lists and mangling rules to crack the most passwords. Some of the classic tools, Alec Moffat's crack, John the Ripper, Loft crack, have all been around for quite a long time. And the classic defenses against this, the recommendations that we would always make, and how we as an industry would always make of how to make yourselves more resistant to these techniques. Well, password complexity rules. Most things like online websites may not even bother with any of this because they are more worried about turning away potential users than they are about keeping their users that they have actually safe. So, but in enterprise environments, you end up with password length minimums, complexity rules, and password rotation. In order to do password rotation, you have to keep histories. And what we hypothetically, and we as the security industry have been telling people forever that they should use stronger hash types. We shouldn't use Unix descrypt, we should use FreeBSD MD5 hash or SHA-512 or bcrypt or whatever. And we shouldn't use NTLM, we shouldn't use LANman. We shouldn't use NTLM either, but it's another story. And so in theory, we have lots and lots of much better choices for password hash types. But their actual adoption and use in the industry is pretty pitiful. So what has this led to? Like, what's been the last 5 or 10 years worth? What's been the story is the attacker's advantaged. Like, over time, the advantages for the attacker have grown faster than the defensive tools that are available to us in trying to manage trying to manage networks, trying to make the work of the attacker a little bit harder. The enterprise password strength rules that I just talked about turn out to have nothing but they're unintended consequences all the way down. They create vulnerabilities and they create weaknesses in user passwords. Moore's law has been really helping the attackers because we're still using hash types from 20 years ago in actual production. We have fantastically great, much slower and therefore stronger hash types available to us, but we don't actually use them in enterprise environments. And that's because the enterprise software vendors just have not kept up. So why do I say that corporate password policies can hurt us? Well, my coworker Rick Redmond has entire talks on this, as I mentioned. And what it boils down to is users, when given a set of standard rules of here's how to make a strong enough password, they address the requirements that are put on them in predictable and similar ways. They all, or at least in very large batches, do the same thing when presented with the same rules. And so an attacker who figures out that what's somebody going to do if they have to have mixed case? They're going to uppercase the first letter of every word. And then what are they going to do if they have to have a number? They're going to put the number at the end. And what are they going to do if they have to have a special character? They're going to put a special at the end. And by the way, the number is probably going to be the year or the month, and the special is probably going to be an exclamation point. So don't raise your hand if your password is a word with the first letter uppercased, followed by a letter, followed by numbers, followed by a special, probably an exclamation point. And what's worse is once a user picks a password that they think is safe, and heck, maybe it is. I mean, they could, maybe they do come up with something that is not just like everyone else around them. But then the following month, we make them change their password. So they make the minimum possible change or some other very predictable change that they can remember. And the next month they do it again and they do it again. So they go from 1 month to the next or 1 season to the next, or they increment a number that's embedded in their password. Or this last example is basically they've literally shifted their fingers across the keyboard by 1, but otherwise the passwords are identical. There's not a single letter that's the same character in the same position between those last 2 passwords, but all they've done is shifted by 1, and it'll be trivially crackable. And the attackers know this. Meanwhile, like I said, we're still using the same hash types that we were 20 years ago on way too many of our systems. And they were too weak then, at least some of them, were too weak at the time, and yet we've not done anything about it in the years since, while the attackers' cracking performance has increased dramatically. And in particular, the advent of GPU cracking has just blown away, all previous cracking records, and it just gets faster all the time. There's also the rise of attacks and attack vectors by which you don't have to actually crack the passwords at all. So pass the hash attacks and things like that work in some environments, in some cases, or for some attacks. That's an entirely different talk that I'm not going to go there. So, like I said, dumb, naive brute forcing it historically wasn't worth your effort. Now, for the shortest and the weakest hash types, it actually is conceivable to do something, and it's not just conceivable, it's fairly easy and cheap to brute force, let's say, the entire NTLM key space for 8-character passwords in just a few days. Once you go from 8 to 9, it gets respectably slower, but you could still, if you parallelize, you can still exhaust the entire key space in not that long. But once you get longer than that, trying to brute force the entire key space of NTLM at 10, 11 longer character passwords is just silly. It's a gigantic waste of electricity. But fortunately, you don't have to. Attackers have figured out that users gravitate towards similar looking passwords. And if the attacker can focus their efforts, and they do, on just the patterns that are most likely to have been used, then they'll crack a disproportionate percentage of users' passwords in a very, relative to the overall total key space, a tiny amount of effort. So I'm going to go into a lot more detail on that. And then PathWell is a set of defensive tools that turns this same relationship against the attacker. So I'm going to adopt the syntax that the Hashcat tools use of using a U to represent any uppercase, an L for any lowercase, D for a number, and S for any special character of punctuation. And so all these examples of password 13, November 24 at Redskins 99 pound, they all have the same pattern of a single uppercase followed by 6 lowercase, followed by 2 numbers, and then a special. Hashcat would represent that as $U, $D, $L, etc., etc. I'm just going to drop out the question marks because all I want to talk about from here on, for the most part, is the topology, the pattern, the mask, etc. So we'll just drop those out; they're redundant. So UD, LLLL, DDS. If there's 4 possible character classes per position, per length character in a password, that means there's password length, there's 4 to the length, to the power of the length of the password, different possible topologies of that length. 4 characters is 64K, 9 characters is 256K, etc. I talked just now about how an 11-character password would take a pretty crazily long time to brute force the entire key space, 8,900 years. But if we pick just a single topology in the 11-character password total key space, and we exhaust all of that, we can do that in a matter of hours on not a very fancy or expensive GPU cracking box. So if it is true that users disproportionately gravitate and clump in specific topologies, spoiler alert, it is, and if it's true that attackers have figured out what those topologies are, they have, then they can destroy 11-character passwords. They can crack enough of a population of users' 11-character passwords in a tiny amount of time that they'll get whatever they want. So, as I just said, if we find that this relationship is true, it's true, then we will destroy things. So CoreLogic does a lot of penetration tests and security assessments, and we crack every password we come across during an engagement because it'll help us get further in the engagement, but then also after the fact to report it back to the customer and say, here's the strengths and weaknesses we see, et cetera, et cetera. And we took that at a larger scale as part of the PathWell project. Our first stage was, how prevalent is this? How frequently do people cluster on predictable topologies? So we analyzed a number of data sets. Here's the first one I'm going to talk a little bit in detail about. So in this enterprise that we tested, it was a food and beverage company. We had a little over 250,000 logins, and that includes history entries. So there weren't actually 250,000 users. There were somewhere between a tenth and a quarter that many actual people, but then there were multiple history entries for each of them. But the history entries are totally valid, because if I crack your password from a year ago, I can guess what it is today with, or at least for a large percentage of users, with pretty good accuracy. So we flattened all of the plain texts that we had cracked, which was over 99% of the plain texts for this organization, and said, how many different topologies do they use? Well, there were only a little over 7,000. Every single user password fell into one of these 7,000 buckets. The most popular, we had 33,000 users whose passwords were upper, 5 lower, 2 digits, followed by upper 6 lower, 2 digits. Overall, over 12% of users had that most popular password topology, and over 12% had the next most. Overall, the top 5 patterns were used by almost 50% of their users. So in order to crack over 50% of their passwords, I only had to crack 5 topologies. Done. If I cracked the first 100, yes?
What can you tell us about the 500 that you didn't manage to crack?
I can't tell you much about them except to tell you that they were harder than the rest. No, it's actually it's an excellent question. So the question was, what can I tell you about the 500 that we weren't able to crack? And that is all that I can tell you with certainty, is that we didn't crack them. I can also tell you that we exhausted everything from 9 characters down. So therefore, we know that they were at least 10 or more. Now, we cracked lots and lots of 10 and 11 and 12 character passwords. They were the easy ones. It was important to us in this analysis that we picked only places where we had an extremely high total crack percentage. Because these numbers, when I say 12% of users, 12.7, 10.6, I'm not comparing that out of the subset that we cracked. I'm comparing it to the whole, including the ones that remain unknown. So within that organization, there are a few hundred people who picked really good passwords and go them. Or maybe they were randomly generated 14-character service passwords. Yep.
How much of the passwords were you able to crack after going back and viewing the history and generating new rules based upon what you were able to crack previously versus what you got initially?
So the question was, how many of these were ones that we were able to crack only after doing initial cracks and stirring the results of the plain text that we'd already cracked and saying, okay, generate new rules based on those, or generate new variations but use just this as the dictionary. Unfortunately, I don't actually know, because we didn't start keeping such good track of that data until later on in our process. Like, we'd already gotten past 99% by doing that recursive cracking approach before I sat down to do this analysis. In general, though, and I said it before, and I should have had some specifics to be able to give you to back up the example, because I claimed earlier that that's one of the things we do. Well, that is one of the things we do. Rick does talk a little bit more about that in some of his longer talks, and I have some links to his talks at the very end. But in general, what I can do is induce by looking at all the plain texts once I've cracked them and say, these plain texts look very related to these ones. Either they've literally changed only one letter or number, or for some other reason. Yes?
So let me follow up my question. Can you tell us anything about the users of those accounts that you couldn't? Were those service accounts, or were they specific maybe to a policy that they had, that certain types of accounts would have certain character-length passwords?
Mm-hmm. So the question was, again, of those ones that we couldn't crack, did we go back and look and find any commonalities about, or relationships or properties of them that we could say, okay, well, apparently users in this particular privileged group are required to have longer passwords than everybody else, or and I threw out the possibility that some of them were service accounts with randomly generated 14-ish or whatever character passwords. So you would do that if and I think we did at the time, but I don't recall it off the top of my head. If we were when we would do this for an organization, that would be part of the things that we would try to figure out about, well, what were the outliers, like why were these outliers? Are they in fact just sort of, you got lucky and these are randomly smart, extra paranoid users? Or, do you have a policy that domain admins have to be 15 characters because that way for instance, that even if you've failed to configure any of your Windows systems to not have landman hashes, if the password is 15 characters or more, there will be no landman hash stored. So a lot of organizations will do that. They'll say our domain admins have to be 15 characters. Now, if their 15 character password is, my password is strong, we'll probably still crack it. But if their 15 character password is reasonably complex, we won't have gotten there. And I think you had a question too?
I was just curious exactly how many people with 4 digits at the end were between 1950 and 2014?
The vast majority, yeah, absolutely. There are some very clear patterns that emerge in the choice of what the digits are. If there's 4 digits in a row, it's almost always a year, and it'll be either the year they were born, the year their kids were born, the year they got married, or the current year. Similarly, an extremely common root word is a month, because if I have to rotate my password every month, I'm gonna put in January and February and March, and K-rat them up a little, but again in a way that my coworker Rick likes to call it the special snowflake. Thank you. Yeah. Everybody thinks they're a special snowflake. Everybody thinks that their little mental shortcut is something that nobody else could come up with. Everybody uses the same approaches. So, but like I said, that's another talk. The bottom line was, we didn't have to do the traditional word list rules approach. We just figured, if you knew ahead of time which topologies were going to be incredibly common, just do those and you're done. And by the way, another couple of things that emerged as we studied the data. The difference between the most popular and second most popular, and the difference between, I think, the third and fifth most popular, is the addition of an extra lowercase letter in the middle. We looked at this and we guessed and we asked the customer and they said yes. In fact, the case was that over the course of the last year, they had increased their minimum password length requirement by 1 from 8 to 9. And so what did people do? They just use a slightly longer word than they'd been using before. So that is a theme we see over and over. So not only can previous password hashes, from history entries tell you something about what's going to come next, but when the policy changes, it's not really effective until your entire history has been rotated away from and purged of the old. And it just again reinforces that users are going to make a very simple and similar change. Now, one way I wanted to visualize this data was, and speaking of visualization, I'm glad Liam is back. I love Liam's talks, but I feel bad going after him because he has these awesome, pretty slides and cool animations and graphics and stuff. I have like the ugliest slides ever. And this isn't my pretty laptop.
But you have great data.
Thank you, I do.
This is awesome.
Thank you.
This is like months and months of work that you could generate all these stats.
Yeah.
This is awesome.
Thank you. Oh, and I should say, in case I forget later, I'm not doing it this weekend because this coming weekend is when I'm finally going to celebrate Christmas. But but sometime in the next month or so, I'm going to publish a slightly edited version of a deliverable we did. We did all this work under the Cyber Fast Track program. Our first deliverable was a big research project of doing all this analysis and feasibility study of, is this worth doing, and then how would we do it? So we're going to try to squeeze out of that existing 70-page paper something smaller but still quite meaty that we'll put out as a white paper. So, and it'll have a lot more of these details in it. But yes, I had so much fun with the data in this. Anyway, yeah.
Have we ever looked at the cross-pollination between base words with different users in the same company, if there's a correlation?
So the question was, have we looked for differences in correlating the base words chosen by different groups of users within a company? I think indirectly we have, in that anytime we're studying a particular company, we will, and this is also eats a little bit into Rick's a number of his talks. We'll always study like what's the company's industry, what are the locations that they have their main headquarters and offices in, what languages do their user population speak, if they're not all like if they have international offices, where are those offices? So, you know, if we find that they've got developers from India, let's throw dictionaries of Indian names and rivers and blah 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 and cities and historical events, and we'll find hits from that group, or we'll find the names of sports teams from, you know, whatever the cities that they have offices in. What we probably don't do, but it would be fruitful, is to study by business unit within the organization. Like throw together a dictionary of actuarial terms and use that when doing the analysis of the accounting department, or you know, statistical terms when you're looking at like financial analysts, stuff like that. I'm pretty sure that would pay off. I have to finish explaining what I was going to do here. So. One of the things that I wanted to visualize, and it goes back to the name PathWell, which is password topology histogram, and we'll talk about the where leveling in a second. If I took these frequencies, the topmost topology is used 12.7, and then another 12.7, and then 10.6, and 7.3, and 5.0, and then all the way down to a really long tail, that's what it looks like. Ignore the numbers on the x-axis. They're relatively meaningless. They're just unique identifiers that we had assigned to each of the possible topologies. But the point being, the most popular topologies are super tall. I mean, there's 7,000 possible topologies. I'm only showing the top 50. Most of them are zeros. I mean, most of them there's 7,000 that are in use. There are about 1 million possible. So if this graph were to scale and showed every possible topology along the x-axis, it would be 22 miles wide. And instead, we've got all these users clumped in very specific topologies. Another example. This place was using slightly better hash sets. We didn't go after their Active Directory. We went after their enterprise LDAP, and it was using salted SHA, which is a good deal better than NTLM, but that's not saying much. So we cracked not 99%, but somewhere upwards of 90, in the low 90s. But that was still enough to produce some pretty interesting data. More unique topologies here, but still quite a bit of repetition. Instead of the top topologies being used 12+% of the time, they were used 4 and 5, 3, 4, 5. Well, okay. I mean, that's a lot better than the previous example, but it still suits our needs because the top 5 topologies still crack 16% of all passwords. So once again, I exhaust top 5 topologies, and I'm going to get 1 in every 6 users in the company. And the top 100 get me over 60%. They too had recently strengthened their rules. Can anybody guess what changes they had made?
Added a special.
Damn it! I put it in the bottom of the slide. Can I? If I cover it here, can you see?
Obviously, you don't read the bottom.
Yes. Yes, it is. They had added a special, and they'd increased the length requirement. So they didn't do both. I don't know if they did both of those changes at the exact same time, but you can, if you study the data long enough, you could probably tease out, well, 6 months ago, I see people added another character, and then 3 months ago, I see they started adding a special if they didn't already have one. So that's the, so all kinds of interesting things you can figure out just by studying, studying a dump like that. Their graph is not quite as peaked as the earlier, but it's still nowhere near flat. And we can still exploit this relationship. Oh, and notice the very topmost pattern there, ULLLLDD. Well, before they had strengthened their requirements, their top pattern was the exact same as the other one. And then, yes, when they added a special, they added, they tacked S's to the end. But in general, we found this, well, we wondered, would that show up in other organizations? Now, that was our first 2. What about in any place that requires that you use all 4 out of 4, there are 4 lights, all 4 out of 4 character classes, would we see the number 2 here of upper, lower, 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 digit, digit, special And if you only required 3 out of the 4, are we going to see the same thing? Upper, lower, digit. Yes. This is a graph of 8 different enterprises where we'd cracked 90+%. And each color is a different organization, but the x-axes line up here. So any bar that's stacked with lots of different colors means that that pattern occurred a large percentage in every one of the organizations. And the tallest overall are the ones that were very common in every organization. This is the top 50-ish. So if you were to take the top 10 of these and use them as your top 10, your first 10 anywhere you ever went, ever, at least in companies in the United States, they would probably all get really good success rates everywhere we went. Yes?
What's that light blue one?
Same question. Okay. Yes, good. I'm glad somebody noticed that. So the light blue one, I said before that the x-axis, the actual assignment of numbers didn't mean anything. It actually has a boring under the hood meaning, but the peculiarity that this turns out is that the bar that happens to be really tall light blue is I believe it is a upper, lower, meaning only 2 character classes were required. And what this tells us is, number 1, only one of our 8 enterprises had password policies so weak that users didn't even have to have 3 out of the 4. And number 2, if you allow users to only use 2 out of the 4, they will all choose the same terrible pattern. So it reinforced our idea. However, if you didn't know going in what policy a particular organization allowed, it probably wouldn't be worth your time to put that on top 5 list, because you'd spend time trying to exhaust that pattern when in fact most organizations wouldn't have allowed any user to use that pattern. So in general, yeah. Oh, sorry, yeah.
How often do you see non-alpha characters?
Very rarely, and it's awesome when we do. And I bet that's one of the reasons for some of those 500 that we never cracked, because we were going for bulk law of averages kind of stuff. And so I should back up. The question was, how often do we see non-alpha characters in passwords? If there's a substantial percentage of the user population that speaks a particular non-English language, it can be worthwhile to put their characters, like the French-specific characters or the Spanish-specific characters. It can be worthwhile to include those in your analysis, and because a decent percentage of people will use them. But like the Alt-25, the Alt number pad trick of including a non-printable nonsense character in your password is awesome and defeats most password crackers. Not because they can't crack it, but because they don't bother to try. Now, unless a huge percentage of your users do that, the attacker doesn't need to adapt to it. He just moves on and cracks everybody else. If a large percentage of your users do it, the attacker will probably figure out when nothing cracks and try to include it. But it does raise their workload substantially. The problem is users will, there's a hardening versus users lynching you continuum. And I try to stay away from that end of it. I've never actually been at a place, excuse me, that required that to be part of users' passwords. It would be interesting to see what happened if you did try to enforce that. But what it does mean is that as an individual, one of the best things you can do to piss off pen testers is at least make sure that you don't get embarrassed when the report comes out and have your password be one of the ones listed, is to do that, include non-printables in your password. So I pretty much talked to all of the stuff on this slide. And just as another data point, I said, well, okay, well, what about 15 character passwords? There are certain organizations who have policies that say passwords must be 15 characters or longer. They must have at least 2 uppercase, lowercase, digits, specials. That should be awesome and super hard to crack, right? I mean, it would take, let's see, I didn't include it here, but I did the math last night, and it would take, in order to exhaustively brute force the entire 15-character NTLM password key space, for instance, it would take until the heat death of the universe. That's pretty good, but...
Yeah, but you get it.
Well, you get it, yeah. Yep. And because they're not salted, you only have to do it once. Did you have a question?
Just the
I'm sorry?
That's just Latin alphabet.
Yeah, that's just Latin alphabet, like 95 possible, characters per position. But if I only need to crack one topology, if I am correct in guessing that there are a couple of topologies that, again, users are going to gravitate towards, even in 15 character space, and if I focus just on that one topology, I'm still going to be able to crack, using my relatively cheap cracking rig, I'll be able to crack on average for a 100,000 user population with 9 history entries per user, so 1 million hashes in my list. Let's see, what did I guess? I said if 1% of users use that topology, and remember before, our top topologies were used by anywhere from 5 to 10 to 12% of users, but a 15 character space, maybe there's more room for them to spread out, maybe they don't clump quite so narrowly. So we'll say 1% of users use that topology. We would end up cracking on average 1 every 81 hours. So usually organizations sort of try to balance their password length requirement versus their password rotation requirement to say we want users to rotate their passwords regularly enough that you can't crack our average length password, our minimum length password before they've been required to change it. Well, you better make your users generate new 15 character passwords every 81 hours. Good luck. And again, most users will make the minimum change from one password to the next. So once you have successfully cracked one, even if it is a history entry, that gives you a leg up to trying to crack the newer ones. Okay, so this is all doom and gloom, and everybody sucks, and we should all go home. We should just cry and ourselves to sleep at night. So let's fix it, shall we? So the defenses need to evolve. I've been talking about how the attacks have evolved. The defenses need to evolve to protect against the new reality. And the old rules are not bad. Minimum length, minimum complexity, no dictionary words, even not rotating or repeating passwords are all decent things. But we definitely need something that can take into account and protect against this common human behavior that leads to enterprise passwords being trivial to crack. So at a sort of speaking abstractly, what could we do? Well, we could blacklist the most common topologies. That would be a good first step, but if we just stop there, then it's the attackers will catch up with us and we'll be back where we started. And I go into a little more detail on that in a second. We could prevent users from reusing the same topology. We could prevent a user who's changing their password from choosing a new password that uses the same topology as the last one, or even one that's that's only one change away from their last one. Yes?
If you were to change the topology so that the user can't use the same one twice, wouldn't they just add a number somewhere in between?
Probably. They would probably just add a letter, because adding a letter in between would be one way of changing the topology. Now, if they are going to do that, the attacker needs to guess which position they've added. So they basically, to go from one topology to anything like it would be one hop away. And I do get into some more detail about that in a minute, so maybe I'll wait and finish answering your question later. Yes, first you and then you.
I was going to ask how you track topologies, but I thought maybe password changes.
Yeah, at password change time we gather some stuff, and I'll talk about that in a second. Yep.
But if you're storing that many topologies, wouldn't you essentially be storing the per user topology delta, and then I just attack your server?
That is, so exactly how much information you store and how you store it, and whether it could be attacked by an compromised by an attacker is a potential way to give away information that in turn makes it easier to crack. So I will also address that in a second. So first, behind him in the red, and then you.
Go to the same question.
Oh, okay. So I'll get to it in a second. Yes?
So will you also give us sample wording to explain to users what a topology is?
No, but I have a big slide where I say like one of the remaining hard parts is user acceptance and user hinting and all that kind of stuff. Right now it works as a technical toy, but I think, you know, yes, you'd be on the lynching side of that continuum I talked about before. The phrase topology wear leveling. So I go back to that idea of that that histogram where we had like a really tall spikes and then, you know, and then it dropped off. Ideally from the perspective of the defenders trying to make their passwords harder to crack, you'd want to see a flat graph. You'd want like no topology to be any more particularly likely to be in use than any other, so the attacker has no advantage. They can't take a shortcut to attack just the most common ones. So if you've achieved any levels of success in this approach, what's your level of success? How much harder have you made it for the attacker? And we did a bunch of hand-wavy math, and it's in the white paper that I'll hopefully publish later, about the best case is when the sprinkling of users across the possible topology space is indistinguishable from random. And that's not impossible, but it's not super likely. But if that's the best you could do with this. And the best you could do is to make it about 6 orders of magnitude harder to crack. I measure that both in spending a certain amount of computing effort, hours or months of CPU time, cracks, you know, 100,000 passwords, 10,000 passwords, on average, 1 password, 0.1 passwords. You crack 1/1,000,000th as many passwords using the same amount of cracking time. Or if your goal is to crack a certain percentage, let's say 30%, which was much lower than how many we could crack, we know, by cracking just 5 topologies. If you say my goal is to crack 30% of all the passwords, it would take you up to 1,000,000 times as long to accomplish that. That's the best case. The worst case is the situation in which the attacker compromises your back-end data store where you're tracking which topologies are in use and their use counts. No!
I didn't think that was going to be popular.
The worst case for the defender, when the bad guy has owned your PathWell system and you're tracking all the metadata that we are capable of tracking, so that the attacker gets as many hints as he possibly can, he still has 2 to 3 orders of magnitude more work to do and less effectiveness in his cracking efforts than in today's non-PathWelled system. And then the realistic case is somewhere in the middle, 4 to 5 orders of magnitude. When I say realistic case, I mean users have spread out. You're not allowing them to use the most commonly guessable topologies, but they're not pure random either, and the attacker can take advantage of that and make educated guesses about which topologies to target. One interesting property is if, let's say, you're only allowing 1 use per topology, one active use per topology, then when the attacker knows, well, I'm going to target upper, lower, 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 digit because it's, you know, everybody wants to use that, so I'm going to try that first. If he does succeed in cracking 1, he can probably quit and move to the next one right away. But that turns out to not be a huge savings on his part, because conversely, he has to exhaust the entire thing. If there isn't a password in that space, he has to exhaust the entire thing before deciding to move on. And maybe there's some cool games he can play where he decides to optimize and say, okay, well, at 50% I'm moving on whether I've succeeded or not, you know, etc. But that might get him a power of 2 work factor improvement, but not a power of 10 work factor improvement, which is what we're going after. I mean, when I say orders of magnitude, I'm talking about powers of 10. So that's the hypothetical fully wear-leveled graph. Keyspace reduction. One of the costs is that we are making some passwords, in fact, a lot of passwords, impossible to be used by users. If we blacklist the top 100 topologies, that means no password that fits that pattern is ever allowed to be in use by anybody. So one of the very first questions, and I'm actually surprised no one has asked it yet, is what does this cost us? Doesn't it make the attacker's life easier to know that he doesn't have to try any of those passwords? Assuming he knows that we're using a PathWell system, and assuming that he knows what the most popular 100 topologies are. Let's say we've used a blacklist of the top 100. How much does that cost us? The answer is very little. If, like I said, there's 8 to the 4th, It's backwards. They should be 4 to the 8th. Ignore the bird, follow the river. So if there are, it works out to the same thing. If there's 64,000 possible topologies and we've blacklisted the 100 most popular, we've cut out less than 1% of the possible topologies, or possible key space. We've actually cut out about 0.2% of the possible key space. If we are only maintaining a blacklist of around 100, but we actually are enforcing a minimum password length of 9, 10, or something along those lines, then the percentage that we've excluded is even smaller. So the attacker might be able to save himself 0.1 or 0.2 or 0.01% of the work. And that's our cost for forbidding the attacker from cracking 10, 20, 50% of passwords by just cracking 5 topologies. I'll take it. I'll take that any day. I thought I had another. Yes, okay, right. So another thing that we're doing is when we force topology uniqueness, again, that means that as soon as a user has used a certain topology, no other user is allowed to use it. Or maybe our max use isn't 1. Maybe we allow 2 or 5 users to use one topology, but we cap out. So the downside of that is that for any given user population, the odds that any randomly selected topology is going to have at least one password in it goes up. And that effect gets even worse the more users we have. If we have, for 8-character passwords, 65,000 topologies. If we have 60,000 users, almost any topology you pick is going to have a user in it. But again, we're comparing this to when the attacker can target one topology and get 5% of all users, boom. So that case is so bad that this case is so much better that that cost is probably worth it. And now this effect also gets better for us, the defenders, when we have longer passwords requirements because there's more possible buckets for users to move into. Conversely, it gets worse, like I said, the larger the user population. All right, so I'm going to have to blitz here. Damn. So in the Crack Me If You Can contest, we've been running this password cracking contest at DEF CON for years now. And this last summer, we included a subset of the data. We didn't want to skew the results of the contest, but we did want to see what would happen if you gave password crackers data sets that had been manipulated according to some of these concepts without telling them that it was done. And so in the contest, we had the data sets, the password hashes that everybody was trying to crack, split into quote-unquote companies. There were just, different buckets of passwords. Companies 1 through 5 were not related to the PathWell experiment, and they were the majority of all the passwords used in the contest. Companies 6, 7, and 8 were different kinds of measurements we were taking of experiments. Company 6 followed the exact same bias distribution that we had seen by percentage in our earlier slide with the 8 companies merged together. So the top topologies were incredibly overused and then sort of falling off from there. Company 7 was where leveled. No topology was allowed to be used more than once. However, the topologies chosen, there was no blacklist, so the most popular topologies were chosen. And then once a topology had been chosen, the next topology used by the next user who wanted to use that same one was assigned the next closest one. And then the next closest one after that, and back and forth. So in other words, it's the way you would expect users to behave if they weren't allowed to reuse a topology, but you had no other constraints on them. They would choose the minimum possible change that the system would allow them. And then company 8 was entirely randomly distributed across the topology space. And we further split them up into different hash types by length of the plaintext. Now, in no world is NTLM safe to use for passwords less than, let's say, 10 characters. 9 is, shall not be the number of thy counting, and 8 is right out. But we had to keep the contest interesting. We had to have some cracks in a 48-hour period. So we did allow 9-character NTLMs. The summary of the feedback we got from the teams was, what the hell is company 8 doing? We couldn't crack a single one. And in fact, the contest was split into pro and street. The password plain texts were different between the two, but the relationships in the derivation were actually the same between Pro and Street. But this was just a way that the team self-sorted by how much resources they had and who they wanted to be competing against. And as you can see, going from the control to wear leveled but entirely predictable was about an order of magnitude drop off. The more fully implemented PathWell data set, Company 8, fell off anywhere from 3 to, I can't count them, orders of magnitude, because they were so hard people just got all zeros. So I can't tell exactly how effective it was, other than that it clearly was. Okay, so PathWell itself, like, what did we do with this? We built a PAM module that implements optionally all these different control options that I've been talking about. The audit mode keeps a database of whenever a password is changed, and all of these are optional, like I said. So there are security ramifications of enabling audit mode. You don't have to enable audit mode. Every time a password is changed, we increment a counter for the topology that password was using. And if you do nothing but this, then you get, over time, you can build up your own graph of how skewed your environment is. It's also useful in some of the other modes, the enforcement modes later. The database is sensitive and you don't want it to get stolen. We thought about, when a user password is changed, decrement the counter for their old one and increment the counter for their new one. The problem is that leaks a lot more information to the attackers if they do get your database. And in general, it just had a lot of corner cases. What if an admin changes a user's password instead of the user providing their old one at the time of password change? And we said, you know what, we don't need that. Let's just go forward like this. The current implementation, like I said, it's a Linux PAM module, supports plain text up to 29 characters long. 29 characters ought to be enough for anybody. Famous last words. Enforcement modes. Well, I've talked about blacklisting a bunch. We do that, and we built a default blacklist, but people can build their own and substitute it or whatever. It's not enough, because what will happen if you just blacklist over time, and eventually users will, instead of using what they're used to all clustering around, they will all herd somewhere else, and then we'll go to the next nearest, popular topology, and they'll all settle down there, and the attackers will find them there, and they will kill them. But it would take a long time for that to happen, and you don't have to run faster than the attacker. You just have to run faster than the other guy that the attacker is attacking. It's just like the bear. Maxed use. So this is the tunable that says a topology can only be used n times, and typically you would do 1, but maybe you'd do 2 or 5 or whatever. And that requires the audit database to exist, because it can't check to see if it's already in use unless you're auditing to keep that database built. Minimum lev, okay. This should be its own freaking talk. But Levenstein distance is also sometimes called the edit distance. It's the distance, the number of changes to get from one string to another string. And in our case, we are talking about the minimum number of changes in a topology to get from one topology to another. And if you only change one of the characters in a topology, that's a lev distance of 1. If you change 2, it's a lev distance 2, etc. So the idea is, you might want to enforce that not only if a user changes their password does it have to be at least a different topology than the previous one. You may want to say it has to be at least 2 changes away from the previous one. Yes?
What if you just enforce that and not the minimum password changes? And that way you don't have a table that can be...
Exactly. So you could get most of the benefit of PathWell by just having a blacklist to cut out the most common, like, world topologies, and then a minlev of, say, 2 or more. That would do a great job in spreading out your user password hash or your user plaintext selection across the possible topology space without having to keep this incriminating record of your own of your own user population. So that is a combination that I think that a lot of places should consider. Okay, users reception. Lynching. We need some test beds to do audit stuff to see just how bad this is. Is just our enterprise customers. Maybe they're maybe they are skewed and worse than most of the world, and maybe that's why they're our customers. I hope not. I hope it's the other way around. They're smarter than the average bear. But anyway, we need more user populations. We also need people that are interested in letting us try out. Yes?
I would suggest password managers have to have a key to access the password,
Mm-hmm.
and therefore their customers might actually be motivated to participate.
Well, what's interesting, so the question was, would companies that make password managers be, they'd have a motivation to make sure that the passwords are strong, so would they have an interest in this? I'm not sure, because the nice thing about a password manager, I love password managers. I recommend, I don't want to endorse a specific one, because tomorrow that one will have some 0-day posted and it'll be my fault. But I love password managers because it allows you, the end user, to have just completely crazy disparate passwords for every system you ever touch. I don't like the ones that are cloud-based and where their back end has your secret stuff, but that's another talk. In general, enterprise identity management systems, the software vendors that have brought us these terrible hash types would be the great place to go for something like this, except that I don't know that they're motivated to do so. Let me, since I'm out of time already, and I have just a couple more slides, but then I'll get out of the way, let me just ask that we take questions outside, because I'm already past time. User hinting is one of the things I think we have to have or at least we have to have options that will help offset the mob. Telling users your new password candidate failed because of XYZ. Everything you tell them potentially tells an inside malicious actor things that you may not want them to know. The cost benefit needs to be analyzed a little bit more about what information are you giving away, how much is this helping the attacker versus how much help must you give the users in order for this to be viable. Not a demo. So the whole thing is, like I said, PAM modules. We hook in either early in the process for the various enforcement modes or late in the process for the monitor, because only if your password change is successful do we want to record the new topology, or both. In the case of max use, we have to both enforce and monitor. And kinds of error messages that go to syslog, not to the user, are, it failed for this, that, or the other reason. And next steps for the project, I already kind of talked about this a little bit. Other platforms to build this on. We need somebody interested in trying to build this or helping us build this for enterprise LDAP, Active Directory, some way to figure out how to make it and sell it. We applied for patent on various parts of this, but I do intend to make the Linux PAM implementation some kind of freely available in source and licensed appropriately. I would not be happy if one of those enterprise vendors took this whole thing, whole cloth, dropped it into their commercial tools, and made millions and millions of bucks off it. But I would love it if more users and more enterprise system administrators were able to incorporate this kind of technology.
What if one of those companies did it and it saved people from getting breached and their money stolen in much larger increments?
Yeah, I would be happy about that, even though I would be sad that, I would be happy to have it out in people's hands and protecting people. So, So the other big question about this next step-wise is, what's the next step for the attacker? If we start implementing this, rolling it out successfully, what do they do next? How's their next evolution of cracking tools and cracking techniques going to go? And maybe the answer is that, they just all stop trying to crack passwords and just use pass the hash and similar things. And so this whole thing becomes moot. But there's environments where that doesn't necessarily work anyway. So that's pretty much all, thanks to a number of my coworkers who, like I said, did more work actually making this a reality than I did. Bit Systems, who managed the Cyber Fast Track program, DARPA, who funded the thing, and here's a bunch of links to things.
Questions outside. if you like them, we're going to...
This has been a presentation of NoVA Hackers at ShmooCon Epilogue 2014, hosted by Mach37, brought to you by ComputeCycle. Video recording and streaming services provided by Cranial Thunder Productions.